one of the major topics of this course is going to be functional programming. So I think it's helpful to see functional programming in its pure and original form. Lisp is a language from the 1950s, created by McCarthy. It's extremely influential. This language was designed to perform artificial intelligence, to play chess, if you will, at a time when the only other existing high-level language was Fortran. And Fortran was definitely oriented towards scientific computation, toward computing trajectory tables for ballistics and things like that. So Lisp was really out of left field. It was motivated by this idea of doing AI, and it's been extremely influential in language development. So most significantly of all, garbage collection comes from this. So languages like JavaScript, Java, could not exist without the prior work on Lisp, and garbage collection in particular. So it's also the first language with higher order functions, nested functions, with a read eval print loop, so you can run everything interactively, with a very sophisticated macro system, much fancier than anything you'll see in any other language. And it even has influence on object-oriented languages by introducing the concept of objects in a way that's not like in any other language, using multiple dispatch and multi-methods. So there's lots of dialects of Lisp. The language has been around a long time, and lately Racket is probably the most recent version of it. Clojure is also quite actively developed. We're going to use a version of Lisp called Scheme. It's been around for a long time, and it's fairly well supported. We're going to write Scheme functions. They look something like this. And you can immediately see from the syntax of, this is something shared by all Lisp-like languages, is this syntax. It's initially really annoying to humans. You get used to it. You definitely need a certain kind of editor. But this leads Lisp to be referred to as an acronym for lots of infuriating and silly parentheses. So when you're going to run Scheme, the easiest way to do it is to go to a website and run it online. So you don't have to download anything. And this is actually sufficient for your homework and for the worksheet this week. You can just go to this site, rebel.it, and they run something called Biwa Scheme. Biwa Scheme is a scheme interpreter written in JavaScript, and you can run, pure Scheme programs here. It's maybe not as convenient as other things for demos, so I won't be using it much here. But anyway, if you type in a program, or you can paste it in, you can hit run, and then you'll see the output of your program. Okay? So one thing I'll warn you though is one of the readings I'm going to give you deals with rational numbers like 1/2 and 1/4. And in Scheme, this is a perfectly sensible program, so adding 1/2 and 1/4 should give you 3/4. Last time I checked, this was not supported by Biwa Scheme. Let's see today if it runs or not. Nope, it doesn't understand it. So just a warning, you'll see rational numbers in one of the readings. If you're using Biwa Scheme, it does not support rational numbers, but no big deal. So that's using REPL-IT. It's quite handy. I use Homebrew on my Mac. So Homebrew, if you click here, is a command line tool for installing lots of software. So you can see here, I've got Homebrew installed, and I can do something like, hey, Homebrew, what kind of versions of Scheme are there available online? And you can see there's lots of them. The one that I'm going to be using here in lecture is called SISC Scheme, and you can also download it directly. There's some notes about that in the worksheet if you want to do that. So I'll be doing this here just to run it. And you can see that adding 1/2 and 1/4 should actually work in this version of Scheme. This is one of the versions out of MIT. So In any case, so once you've got Scheme running, you can play around with it, and you can look at the different kinds of things that exist in the language. It has values such as numbers, strings, and a concept which is not as familiar. It's called a symbol. Symbols actually exist now in Java, but a symbol is a unique sort of identifier. It's used for lots of purposes in the language. So you can think of like the plus sign as something like a symbol. And we can use these symbols to do execution. So the way we write expressions in Scheme is a little bit unusual as well. Instead of writing expressions infix as we're sort of used to, they're written prefix. So if we want to add 1 and 2 and then subsequently multiply by 3, we'd write this in the infix form, in this form. Whereas in Scheme, we use what's called prefix. So we have an expression that includes all of the things that we want to multiply together. And within that, we have an addition. So parentheses are absolutely necessary. And in fact, what Scheme will do is anytime it sees an open parenthesis, it's going to assume that the first thing after the parenthesis is a function, and that we're going to perform the function on the argument. So note that the you would think of writing this sort of like this in a standard language, probably with commas as well, right? So it's the operator plus being applied to the arguments 1, 2, and 3. This makes no sense in Scheme. So in Scheme, it's the operator plus applied to 1, 2, and 3. So just spaces separating the arguments. If you try to just make something like this, it's looking for the procedure with the name 1. And 1 is not a procedure here or a function, so it can't invoke it. Okay, so again, this is sort of the syntax for invoking any kind of function or operator. There's no difference between a function or an operator in Scheme. So that's various things you can do. If an operator is associative and commutative and all that, like addition is, it's quite obvious what's happening here. This is going to give you 17. When you have something like this, you have to wonder what's happening. And the rule here in Scheme is it's going to roll left to right. So this will be 10 minus 5. That gives me 5. And then 5 minus 2, that gives me 3. Let's see if I'm telling you the truth. We'll try it out. And indeed, it is 3. So the terminology that you should know, maybe you've never heard it. This terminology is prefix, infix, and postfix, and these correspond to the different ideas of traversing a tree. So if you think about the tree representing this expression, 1 plus 2, it's the root is the plus operation, and beneath the root we have 2 leaves, which are 1 and 2. So I'm adding 1 and 2. If you visit that tree prefix, then you first visit the plus, then you go to the left child, then the right child, so you'll print plus 1, 2. If you do it infix, you go left first, then to the root, then right. And if you go postfix, you go to the children first before you visit the parent. So this whole idea of operator terminology is deeply related to the representation of expressions as trees. If we have a function, we can call it, but we can also define our own functions. So this is done with a macro in Scheme. So the macro define, it's sometimes also called a special form. So this macro or special form define takes, it's not invoking a function here. So we're not calling the function define. We're instead doing something special. So what define does is it takes the first argument to be the style you want to invoke this function. So in that first argument, it has to be a couple of things: the name of the function followed by any parameters. And then after that, the next expression is going to be the body of the function. Right? So once you define a function in this way, then you can invoke it. and it will have the expected effect. So if I define square in this way, and then I invoke it, I will get the answer, which is the square of 5 is 5 times 5, which is 25. You can invoke it twice, of course, and now you have 25 squared, which I don't remember what that is. Let's find out. This is not going to work when I first run it because square is not defined. So what I'm going to need to do is define the square function. And then once I've done that, I can find out that 25 times 25 is 625. So yay. So that's how we define a function. The general form here is we have the macro name define, then we have a function name, then we have a list of parameters, and then in fact we can have multiple expressions here. And these are going to the meaning here is that we will execute these expressions one at a time. So first we execute expression 1, then expression 2, then expression 3, etc. So we have those im arguments. The body of the function then is a sequence of these expressions, and these are evaluated for side effect. So the first several expressions here will not actually produce a value. It's only the last expression which gives us the return value. There's no return keyword here, though. There's no statements. There's just expressions. And so we're just going to execute these expressions one at a time and return the value of the last one. So this is like the comma operator in C. But we don't actually use the comma. So we're executing each of these expressions one at a time. We can use begin as well. So if you ever want to have a sequence of expressions in arbitrary place in Scheme, you can use the begin keyword, which will, it's another macro, which will execute all of the expressions one at a time and then return the value of the last one. All right, so we invoked a function by supplying arguments. And of course, the function name is immediately after a parenthesis, so this is how we call it. So if you try and invoke the function without parenthesis, what happens? Let's try. And you see you get a funny thing. You actually get two outputs. So you can see in Scheme, I can just type 5, and it gives me back 5. But you can also type a function name, and it just says, well, that's a procedure. Okay, so if you type multiple things in a row, like 1, 4, and 5, it tells you, well, you just typed in 1, 4, and 5. So if I type in square 5, it tells me, well, there's a procedure, and then there's 5. So it's just giving you or telling you what you did. So if you want to invoke the procedure, you need the parenthesis to actually get it invoked. So the order here of evaluation, in general, we don't have simple values. We're going to have more complex expressions. So if I want to evaluate something like the square of 1 plus 2, well, I better not write it like that. First of all, right, because that's an infix notation, naughty, naughty me. So I want to square 1 plus 2. So what's going to happen here is first I'm going to evaluate the expression 1 plus 2, and then I'm going to evaluate the square. So in general, if I have a function with two expressions as arguments, we first evaluate the expressions in order left to right. So first im in this case, then in. Then once we get the values, we'll invoke the function on those values. So again, define is a special form. It's not a function. It doesn't obey this convention. So we have Booleans as well in this language. And so for example, the equal operator here tests numeric equality. So we can define this function 0 in, which tells us whether or not the number in is 0. And we can, of course, invoke that. And what we'll get out is going to be a Boolean value. So let's just run this thing. And so if I invoke 0 on 1, it should tell me that's false. Note it's the hash f, that's the result. And of course, if I ask is 0, 0, that's it. This is actually not a normal name. Normally these names have question marks in them. So a more standard way of writing that would be like that. So predicates, this is a predicate because it returns true or false. And most predicates, the convention in Scheme is to use a question mark in part of the function name. Note that Scheme doesn't do any fancy parsing at all. It takes spaces very seriously. So whatever you have here that's before the white space, it's going to take that to be the name of the function. So functions can have all sorts of funny stuff in them, all sorts of operator symbols and things like that. All right, so that's a zero function. If is a special form, so it's not strict. And the way if works is it is going to evaluate its first argument. And depending upon the value of its first argument, it's either going to evaluate its second or its third argument. So this is a safe divide operation. And it's important that if we have a denominator of 0, that we don't actually perform the division, because this will give us an error. So if we try to divide, 5 by 0 or 4 by 0, we'll get an exception. So if we want to avoid the exception, we need to make sure that we don't do that. And so note that we can tell that this thing is a special form. We can tell it's not actually a function because it's not going to actually perform this division before it does the condition. I mean, that doesn't make any sense, right? So so if we call safe divide, for 0, it's going to work. It's going to say you try to divide by 0. So we're not actually performing that division. We can, because it's non-strict, we can use if to define recursive functions. So here we have the factorial function defined in terms of a condition. Of course, we don't always want to call the second part of the if statement here, the bottom line. We don't want to do that, because if we did that every single time, we'd have an infinite recursion. So at some point, we need to stop calling the factorial function. And the way we do that is using the if statement. So it's really important that the if statement is not strict. It does not first evaluate all its arguments and then determine which one to give the result. No, that's not what it does. Instead, it is going to evaluate only its first argument and then decide which of the two to execute. So if we define the factorial like this, it's very similar to the definition we would get in C if we used conditional expressions. So this is the definition in C of the factorial function using conditional expressions. So here we're just returning the result of performing this test is n less than or equal to 1. If it is, then we return 1. Otherwise, we perform this else part. So we return n times the factorial of n minus 1. So that's the basic sort of scheme types and functions. What I'd like to look at now is the structured values in Scheme. So Scheme actually only has one kind of structured value. It doesn't have arrays and structures and objects and things like that. It only has one thing, and it's called a consel. So a consel is used for any kind of structured value. So the consel holds two things. So for example, we can have a pair of numbers, such as 1 and 2. Note when I cons two things together, I get this thing. This is called a dotted pair. So that's the pair with 1 and 2. I can also cons together some strings or a string and an object, such as a number. So there I've got a number and a string together. And there's two important functions in Scheme. They're called car and cutter. And car, C-A-R, will return the first element of a consel. Cutter will return the second element of a consel. So these are very widely used functions. So this idea of putting things together and then taking them apart is extremely important in programming. So first I want to associate data, and then I want to access that data. So this is the basic thing we're going to use in Lisp, concells. And they're pairs, the way to think about it. We can use concells to represent a list. So what is a linked list? Well, a linked list is nothing but a bunch of pairs. And so here, if I have the list 1, 2, 3, 4, well, what is it going to be? It's just going to be a cell with 1, 2, 3, 4 elements. So what does that look like? And again, we have the car and the cutter. The car is the first element, the cutter is the second in the pair. All right, so how do you do something like this? Well, you build these up using the empty list and then the cons function. So if I have the empty list, I can cons 3 in front of the empty list, and I ended up with a single cell where the first element, the car, is 3, and the cutter is the empty list. So let's actually try that here. So I'm going to create a console there, and it's printed out in a funny way, which I'll tell you about in a second. But what I've got here is that the car of this will be 3, and the cutter is going to be the empty list. Okay, so anytime I do a cons, what I'm doing is putting two things together, and the first element goes in the front and the second element goes in the back. That's it. And when we think about these things, we often think about them as these kind of pointers. All right, so when we have a list, we have, if you think about this is if you like the console with 4 and the empty list. And now what I can do is I can take that guy and put it in front of something else. If we're trying to build up a complex structure like this one or a bigger one, it's kind of handy to have variables to refer to things. So what I can do is let me build this up in 4 statements. So I'll use a variable x4 to refer to the console that holds 4 and the empty list. I'm going to call this x3, x2, and x1. So what we'll do is then put 3 in front of x4, and that'll give me x3. So what I have at this point, if I actually look at what x1 is, it's the list 1, 2, 3, 4. And again, this is the syntax Scheme has for printing out lists. Note that it doesn't print the empty node at the end. So it's just going through the elements and printing the values in the list. So there's the list 1, 2, 3, 4. But this is how it's represented. So we have 4 concells here. One of them has 4 in the empty list. Another one has 3 and a pointer to the second one, or the x4. The next one has 2 and a pointer, etc. So each of them is a console with a pointer and a value. And so anything that has this kind of structure is considered in Scheme to be a list. So if it can sort of traverse it in this form, it'll be perfectly happy. So if you have something that's not like this, then Scheme will not print it as a list. So in particular, what Scheme's looking for is the last console to have its second element to be null. So if that's not the case, if you have something like cons of 1, cons of 2, cons of 3, and now instead of putting nil, I just put the constant 4. Well, this is not a list anymore. This is a rather odd thing, and it's in order to tell you it's not a list, Scheme puts a dot in there. It says, oh, something is wrong. It's not a proper list, and so I just want you to know that's not a proper list. Let me call that thing x0, or let's just call it y. So we're going to define y to be that. And you can investigate x1 and y here. So if I look at the the car of x1, well, what do you expect it to be? 1. Right? The car of the car. What's the car of the car? Well, that's going to be an error because the car is 1, so I can't take the first element of 1. It's not a pair. Okay, so that's wrong. But I can take the car of the cutter. So the cutter of x1, what is it? Well, it's x2. So that makes perfect sense. So what's the car of that? It should be 2. So the car of the cutter here will be x1. Excuse me, it will be 2. This is a very common sort of operation in Scheme. And so we have a shorthand for it. The car of the cutter is written AD, and it'll give you 2. And you can keep going down this way. So we can take the cutter of the cutter and the car, and we'll get 3, and go down 1 more, you get 4. If I try to go down 1 more, it's going to blow up on me because we don't have a value down there. Oh, it's also just mad at me because it doesn't know what I'm talking about. But in any case, it's not going to work. Okay, so that's concells in Scheme. So there's more complex examples you can build up. So if you think about this list here, this is a list with 3 elements. The first element is itself a list. So this is a little bit more complex where my first element is also pointing to a concell. So here I have a list of 3 elements. So that's going to be the list pointing to the second element, which is 21, pointing to the third element, which is also a list. So if you represent this list in memory, this is what you're going to end up with, which is a pointer. Our first concell is going to have 2 pointers, right? One pointing to the list, which is its head, and the other one pointing to its tail. So the tail starts at 21. There's lots of syntax sugar for lists. Lists are very important in Scheme, and so we're going to use them all the time. And the important thing here is we can quote an expression to keep it from getting evaluated. So what quote does is it sort of stops the evaluation from happening. So note that I can't just type in 3 because it's going to think that 3 is a function. I'm trying to call a function. So the way we stop that from happening is using the special form quote. And what quote does is it simply returns a concell holding that expression. So that's nice. What I can do is I can quote in general. There's a quote of a quote. Sorry. So we can have a list holding 3. So this is a list with a single element with 3 in it. And so note that that is different from just quoting 3. So if I just quote 3, I get 3. It's not the list with 3, it's 3. So here I'm quoting a list with a single element. It's clear if I put in more than 1 element. So let's suppose I have 1, 2, 3 elements. Then I get out a list with 3 elements. This is very common, so there's a special shorthand for it, which is to use the single quote. So that's quoting. We can also build up a list by evaluation. So let me give you this example. So this will give me the list 1, 2, 3. So let's do the list 1, 2, 3. Note that this is a little bit different from quote. So if I try to quote here, it's going to be mad because I have too many arguments. So I need to wrap those arguments up. And now if I quote, note that quoting is a little bit different from the list. Okay, because what's happened here in the list is it's creating a list by evaluating all of its arguments. So list is just a function. what list does is it evaluates all its arguments and it constructs a list with those values. Quote is a special form. It does not evaluate any of its arguments. All it does is package them into a list. We can test for equality in Scheme in much the same way we would test for equality in Java or any other language. And just like in many languages, we have different notions of equality. We have different notions of equality in Scheme, like pointer equality versus value equality. Do we want to go through the whole structure, etc.? So in Scheme, if we ask, are these two things eq? We get false, but they are equal. So those are two different types of equality. One thing that's nice about a functional language is that we can understand the behavior of a recursive function just by thinking about what it does to the expressions in the language. So if we have something like this, well, obviously the length here is going to compute, I mean, if we know what the length is, it's going to compute the length, which in this case would be 1, 2, 3, 4, 5. That's what we'd expect. But we can actually watch this execute. So sort of intellectually, it's pretty easy. Let me do a slightly shorter example. Let's just do it with 3 values. So, and let's think about how this is going to execute. Well, what's going to happen here is that the length function is being invoked. So what we're going to do is just take the body of the length function and place it here. But what we're doing is replacing the argument by this list. So we're replacing the argument. So what we're doing is replacing the formal parameter L by the actual parameter 5, 6, 7. So we end up with this. So is this list here equal to the empty list? No, it's not. So what we're going to do then is evaluate to what? Well, we're going to take the else branch. So we end up with this. So what's the else branch say? Well, it's saying we need to add 1 to the length of the cutter. Okay, well, what's the length of the cutter? Well, now, again, this, remember, plus is a function. So we have to evaluate all of the arguments before we can do anything. So what we're going to do is now recursively look at this length function on the cutter of 5, 6, 7. So before we can call the length function, we first need to compute the cutter of 5, 6, 7. So what's the cutter of 5, 6, 7? Well, that's going to be 6, 7. So that's the cutter of 5, 6, 7. And now we can compute the length function on this. So what's that going to do? Well, again, it's going to substitute the body. We're going to end up taking the else branch. And if you'll bear with me, what is this going to return? Well, it's going to return 1 plus the length of 6. Okay, so just applying all those steps again. And what's that going to return then? Well, that's 1 plus the length of 6 here is going to become just what? It'll become 1 plus the length of the empty list. Okay, and now what's going to happen? Well, when I have the length of the empty list, note that at this point, the length of the empty list is immediately going to be returning 0. So this expression here becomes 0, which means now that I've done that, I can come back. Well, this addition can now be performed. So that's simply going to give me 1. Now this addition can be performed, which is going to give me 2. And finally, the top addition is performed, which gives me 3. And that's the result. So the length is 3. So usually you don't go through it in this kind of detail. However, this kind of thinking is actually very effective in terms of understanding how recursive functions execute. It's a little more painful in Java because in Java we don't have nice expressions for these objects and how we compute over the objects and pass the objects around. So having this notation for lists and for computation over lists is actually quite powerful as a programmer when you're trying to think about how your program executes. Okay, so Scheme is a dynamic language like Python. It has dynamic types. And so if you have a variable, you can find out the type of that variable or the value. Excuse me, if you have a value, you can find out the type of a value. So, and there's various types. So symbols, numbers, Booleans, strings, procedures, these are all separate types. And we also have pairs. So pairs are important. And what's interesting to note is that both a proper dotted pair and a list, those are both pairs. So what pair really means is consel. So are you a consel or not? Note that the empty list is not a consel. The empty list is not a consel. It's just an empty list. So in order to be a pair, you need to have two things. The empty list doesn't have that. All right. We also have the list function. The list function tells us whether or not something is a list. And what does that mean here? It means that we're pointing either to the empty list or we're pointing to a consel. And further, if we follow the tail pointers in that consel, we'll eventually get to the empty list. So if you ask, is 1, 2 a list, the answer is true. But if I ask, is 1, 2, dot 3 a list, the answer is false. Okay. So remember, this is the representation of what I'm doing here is going to cons 1 in front of the cons of 2 in front of 3. Okay. Oops. Oh, sorry. In which case I leave out the dot. Sorry. All right, so this is what I'm doing here. And note that this is not a list. So even though the first element is the same, it changes things. All right, so whether or not the last pointer in that thing should actually point to the empty list. All right, so the notion in Scheme, and one of the things that makes it so powerful is this concept of a symbolic expression. So symbolic expressions are these lists with symbols in them that can be evaluated later. And this is really great. So, parsing is defined in Scheme to be trivial. Parsing is always very easy. Whenever you parse, you produce one of these symbolic expressions. So again, it's going to be a list full of stuff that we can execute, or a pointer to a pair that we're going to execute. And as we've seen, quote can be a way of generating one of these S expressions. So when you quote something, you get something that hasn't yet evaluated. So if I perform an expression like this, obviously it's going to immediately evaluate the addition. So this expression is going to result in 3. This expression instead results in a list. First we have the symbol plus, then we'll have 1, then we have 2. So that's the result of quoting that list. What's great about this is we can then manipulate these things. So these symbols, we can put them together, we can find out. So for example, I can construct the same list by consing the symbol plus in front of the list 1, 2. I can ask what's the car of this list, and of course that's the symbol plus. So you can try these things out. So when I quote, what I'm doing is I'm stopping the expression from being evaluated. And conversely, there's a function called eval, which takes its argument and just evaluates it. So it takes an arbitrary scheme program and runs it. And so this is a very powerful kind of dynamic activity you can do. You can construct programs in Scheme and then run them. So if I take this expression here, what is it going to do? Well, we're putting the plus symbol in front of 1 and 2, and then we evaluate it. So this expression is plus 1, 2. When I evaluate, I get 3. So there you go. And you can define functions that evaluate stuff. So for example, this is a function that adds all of the things in a list together. And this is a funny way of writing this. So what I'm going to do is append a plus sign in front of the list and then evaluate it. So that'll add them all up together. It's kind of a crazy way to add up a list, but why not? It actually works in Scheme. The final thing that makes all this work in Scheme is a read function. So the read function reads an expression from the terminal. So I can just invoke read, and it gives me back what I just read. And it's parsing as well. So if I type in the expression 1, 2, 3, it will parse it and return an S expression. And what we can do is, of course, evaluate what we've read. So if I evaluate the result of a read, well, I can type in an S expression like plus 1, 2, 3, and it'll evaluate it. And likewise, we can manipulate the result of read just as an arbitrary list. So I can append something in front of it, and we'll get this result. So let's do 1, 2, 3. And here it's appending plus and then adding them all together. I could also have written this using cons. Right, there we go. And it works the same. So that's Scheme in a nutshell.